Hello, everybody. This is Professor Ali Tarad, and welcome again to your channel, Thermal Engineering Concept and the Principle. In the present episode, we will introduce a series of videos related to the uh, energy and heat transfer in the field of heat conduction in uh, plane where there is sort of heat generation inside the wall. We will apply different boundary conditions depending on the industrial application of this topic. Thank you very much for your support and encouragement throughout the time where we have uh, established a new concept for the relation between you and the channel. Let us start with the objectives of this video. The objectives of the present episode is related to the derivative of three-dimensional heat conduction in a plane wall, uh, reduce the three-dimensional form to one-dimensional heat conduction in the plane wall. Of course, that will be accompanied with heat generation per unit volume. And then we will pass through a case study from the industrial application where we can use the form of this topic in one-dimensional heat conduction, and then we will arrive at the closure of the present video. The derivative of the three-dimensional heat transfer by conduction in a plane wall, let us consider a solid element dx by dy by dz, where it is exposed to a heat transfer process. So we have q sub x for one side, then it will leave at q sub x plus dx at the same direction. We have also, for the top and bottom faces of this element, we have q sub y, which leaves the element at the top q sub y plus dy. And finally, for the third dimension, we have q sub z at the back side of this element, which will leave the element in the front by q sub z d plus dz. So where we can find these applications, I mean, where we have a body with a heat generation. One of them is where you are passing an electrical current through an element section. And that will be just like the um, bus bar, which transfers energy in many applications. And we have the exothermal heat transfer, where a chemical reaction happens, and then that reaction will release heat. And finally, we have the nuclear reaction, where heat can be generated in the material. So, to find areas of these faces, the six faces of this element, we have d sub az equal to dx by dy. Of course, that will be accompanied with uh, a heat transfer rate q sub z and the q sub z plus dz. We have the left and right faces, d sub ax equal to dz times dy with heat transfer rate q sub x and the q sub x plus dx. And finally, we have the bottom and top faces with surface area d sub ay equal to dx times dz with q sub y and q sub y plus dy. These are the surfaces of the element. And finally, we have the volume equal to dx times dy dz. The derivative of the energy equation in a three dimension by conduction is represented by the general form of the energy balance. Thus, on the left-hand side, we have the inlet sides of the element q sub x plus q sub y plus q sub z plus the energy generated in that element equal to the heat transfer left on the other faces q sub x plus dx plus q sub y plus dy plus q sub z plus dz. And if there is any energy accumulated in the body, then we will have d sub e plus d tau, which represents the change in internal energy in that element. So let us substitute the values of these elements of Q in a form. We have Q sub x minus K A x partial t with respect to x. And we have studied that in the previous episodes. And we have Q sub x plus dx equal to Q sub x plus partial Q sub x by partial x dx. If we substitute the values of qx, then you will get finally a form for the q sub x plus dx. Similarly, q sub y can be presented minus k a y partial t with respect to y. And then we have q plus dy equal to q sub y plus q partial q sub y by partial x dy, and then we will get a similar form in the y direction. And finally, in the z direction, we may get the same expression for q sub z plus dz equal to minus bracket k partial t with respect to z plus partial with respect to partial z of the value of k partial t with respect to z dz times dx dy. And we have the heat generation rate equal to q dot, which represents the amount of energy per unit volume times the volume of the element dx by dy by dz. We have also the change of internal energy of that element equal to rho, the density, C, the heat capacity of the material of that element, times the volume dx dy dz times partial t with respect to partial tau, which represents the rate of change of temperature with time. So if we Substitute these values in the general form of equation with the assumption that thermal conductivity is constant, then we will get the final form of the temperature distribution or the energy equation in Cartesian coordinate for 3 dimensions, partial square t with respect to x square, plus partial square t with respect to y square, plus partial square t with respect to z square, plus q dot divided by k equal to 1 divided by alpha partial t with respect to tau. So this is the final form, which should be used wherever you want to use a 3 dimension. And in this equation, we have alpha represents material thermal diffusivity, which is meter squared divided by second, and is equal to thermal conductivity of the material divided by rho C. This equation is a general form where we have taken that Q equal to, the thermal conductivity is constant, and then we may simplify this equation depending on our needs. Can we reduce the general form of the uh, three-dimensional heat conduction in um, solid material? One of the most interesting forms of this equation is the one-dimensional steady-state heat transfer. And this form of equation has many applications in industry, or we may minimize the effect of other dimensions, so we will consider the heat process to occur in one direction. The general form, as has been presented by equation number 2. How can we reduce this equation to the form of one dimension? As shown in this figure, we have the faces, and we may consider it as element with a thickness of L. And if we ignore the effect of y direction, then that means partial square t with respect to y square will vanish and approaches 0. And in the z direction as well, we may have um, partial square t with respect to z square equal to 0. And that will yield um, a form of equation where can be applied in the one dimensional form, heat conduction with heat generation. And this is called the transient form, which is represented by equation 2.1, partial square t with respect to x square plus q dot divided by k equal to 1 divided by alpha partial t with respect to tau. And this form of equation um, it's a general form and can be used even for the case where there is no heat generation. So for steady state, you will get the right-hand side will go to 0. That is, the temperature doesn't change with time. So we have partial t with respect to tau is equal to 0. And the final form will be d squared t by x squared plus q dot divided by k equal to 0. This is the general form for steady state conduction heat transfer with heat generation. To use this equation and to find a solution, we need to execute an integration. The first integration will give us q dt by dx plus q dot divided by kx equal to 0. And if we conduct the second integration, we will get t of x as a function of x plus q dot divided by k x squared divided by 2 equal to c1x plus c2. This is a magic equation where it is used in the one-dimensional heat transfer with heat generation and can be used regardless of the boundary conditions. So I will call this equation a magic equation. Now let us have a case study where we have fixed walls temperatures on both sides. And for example, we have a wall shown in this figure with one-dimensional form, and it has Q dot generated per unit volume inside this body, and thickness L with a boundary conditions as shown in this photo that we have the fixed temperatures on both sides. If we go back to our magic equation T of x, the point or the object is how to find the constants C1 and C2. And usually for this type of equation, we will need two boundary conditions. This is another form just to show schematically how heat transfer is occurred through this wall. And we have Q usually is perpendicular to the surface area of the wall. The first boundary condition we have when x equal to 0, then t as 0 equal to t1. This is boundary condition number 1. And the second one on the other face of the wall, where x equal to L, then we have the temperature equal to T2. Applying boundary condition number 1 and the magic equation number 4 will yield C2 equal to T1. That means you have to substitute for the value of x as 0, and then the temperature is T1, then this will yield C2 equal to T1. And if we apply boundary condition number 2 for the same equation, that will, with the C2 equal to T1, then we will get T1 equal to T2 minus T1 divided by L plus Q dot L divided by 2, which is represented by equation number 9. If we substitute these values of C1 and C2 in the general form of equation 4, then the temperature distribution is shown T of x plus Q dot divided by K x squared divided by 2 equal to the right-hand side in terms of the given values of T1, T2, and other properties of the wall. So the final form is represented by equation 11. We have to prove that this equation is right, is correct. So we will use when x equal to 0, then T of x equal, if we substitute x in equation 11, that will give us the first term on the right hand side goes to 0, and x, the second term will go to 0. Then the temperature T of x equal to T1, which is the same as the boundary condition number 1. And for the second boundary condition, when x equal to L, if we substitute that, then we will get T sub x equal to T2, which is the same value as used in the boundary conditions. The closure, my friends, to this episode, we passed through the derivation of heat conduction equation in 3 dimensions. and one dimension. And this equation was derived for the case where we have a heat generation per unit volume inside the wall. And finally, I have to mention that this application has, or this equation has many applications in industrial applications for heat generation inside a wall. And there is a sort of some resources are listed in a PDF in the description box. And finally, thank you for listening. And if you find this video is useful to you and others, please subscribe and share it with others. So the information can reach anybody who needs it. And thank you. I will see you in the next part of this type of heat conduction with heat generation in a plane wall. Bye bye.